In this video, we're going to talk about internal effectiveness factors. These are applicable in heterogeneous catalysis, where we usually think of the reaction as being determined by the rate of events happening on the surface of the material. However, the active catalyst material is usually dispersed on a high surface area porous support pellet, and in order to react, reactants must diffuse from the bulk through a boundary layer to the external surface of the pellet, and then diffuse through a pore network in the support, and then finally absorb and react to form products at the active sites. Still, there's one more step that these must return to the bulk as products. So the overall rate may actually be limited by external transport, by internal transport, or by the rate of surface reactions. And in some cases, the overall rate may even be influenced by the transfer of heat into or out of the support pellets. So we're going to consider cases where we have thermal equilibrium right now. We're going to focus on the internal resistances, diffusion into the porous support material. So these are internal effectiveness factors in this video. Okay, I want to take just a moment to talk about the multi-scale aspects of this problem. So we've spent a lot of time in the early portions of the course thinking about elementary steps and deriving overall rate laws, really working down at this molecular scale. And then our active sites abstractly become these asterisks here in this diagram that shows the pore network. We just in the last video talked about fusion in these pores, depending on the size and what occupies the pores. And what we're going to do in this video is begin to think about pellet scale and working out for an entire pellet what the concentration profile is as species diffuse down into this pore network and gradually encounter sites and perhaps be consumed by reactions as they penetrate deeper and deeper into the interior of these catalyst pellets. And our ultimate goal, of course, once we have the rate on a per pellet basis and we have the number of pellets in the packing per unit volume, then we can begin to put these descriptions into our reactor scale models and employ the machinery that you all are probably fairly familiar with from undergraduate work. Notice how at every step we build a model of what's happening at the small scale and then really embed it consistently into the balance equations for processes happening at the larger scale. This is a really useful way of exploiting natural time and length scale separations that's quite common in kinetics. The other thing I want to do here is to have a little bit of an unusual starting point. It's a little bit more complicated than just writing down the standard species balance equation, because we really have to think about how all of our pseudo-homogeneous fluxes and our void space and the concentration in that void space enters into the balance equation. So let's think about this equation here. This is the full transient species balance equation, but it looks a little bit different from the one that you're probably used to seeing. The rate of generation of species A is over here. This would be a volumetric number of moles of species A per volume per time. This is our effective diffusivity that already accounts for the void fraction and the tortuosity in the catalyst pellet. We have the superficial concentration of species A in those pores. Remember that this is not really the number of molecules of A inside the pellet divided by the volume of the whole pellet. This would be just the concentration in the pore network. Over here you have a convective flux that looks like the normal term, except that this V has to be a superficial velocity. So it would be like the flux passing through your surface divided by the cross-sectional area of that surface. And similarly, we have to account for void fraction over here when we write down our accumulation term. So we have a changing concentration of species A in the pores, but we want to remember that on a volumetric basis now, there's not much capacity to fill up with species A, and that's accounted for in this little epsilon parameter here. We can drive almost everything that we're going to do in this section by starting with this equation and crossing off the appropriate terms. Most of the time, we're going to be interested in steady state phenomena, so this will be gone. Usually, we can get away with ignoring convective fluxes. That's a perfect approximation if you have molecules in the liquid. It is also a good approximation if you have a gas phase reaction that consumes as many moles as it generates. When you have a situation where one hydrocarbon molecule going in, and a new hydrocarbon dehydrogenated with a bunch of hydrogens also coming out of the catalyst pellet, then you can get some net convection inside the pores, but it's quite common in the literature to go ahead and ignore this term, and most of what we will do in here ignores it as well. I want to give you a couple of references to works that don't ignore this term. There's a discussion of cases where the convection term is important in Bartholomew and Butt in 1991. I'm sure there's quite a few others as well. Okay, so we're going to consider first this case of isothermal reaction conditions and irreversible first order kinetics. From the zero over here, you can see that that we have already crossed off the accumulation term and the convection term in that previous equation that we were discussing. You can also see the spherical geometry. So we're describing a spherical pellet because that is what happened to our Laplacian operator right there. We're going to have boundary conditions. Our spherical pellet is of radius r. And there's the effective diffusivity that we've been talking about in the last video. And the rate of generation of species A here, technically with the minus sign included in the rate of species A. So that's K cat A. This is kind of a deceptively simple formulation. This is usually the starting point in a lot of textbooks, but many details have been lumped into this K cat quantity. So you actually know how to derive this, right? So you know how to work through the catalytic mechanism, write down a turnover frequency, multiply the turnover frequency expression by the number of sites per area on the active material, then multiply the accessible area per mass of active material, then multiply by the mass per volume loading of the active material. And including all of these components in kcat explicitly can be a little clunky, and we're writing kcat right now. But when you do an experimental analysis, you can pull so much more out of your data if you keep track of these things than just writing kcat or kobs, as is common practice in the literature. Really valuable for being able to compare the experiment that one student has done to the experiment that's published in the literature from 10 years ago. If you keep track of none of these details, then in order to reproduce a number, you have to get everything exactly the same as the previous experiment. But if you keep track of these details and your loading is 10% and their loading is 7, you would expect maybe the kcat would be different, but the intrinsic kinetic parameters in that turnover frequency expression should be the same. Okay, let's talk about boundary conditions and non-dimensionalization. At the surface of the pellet, we're going to impose a surface concentration. This might be equivalent to the bulk if there's no external resistance, but in general, we'll just call it Ca sub s. At the center of the pellet, it's not a true boundary. It's really the interior of this domain. And technically, we only require that the solution be bounded everywhere. But you can show using the divergence theorem that a bounded solution at 0 must correspond to a solution with derivative at 0 equals 0. So this is a little cartoon picture of our spherical pellet. I've drawn the radius axis coming out, and the surface is at r equals capital R, and fixed the boundary value at the surface, and fixed the derivative to 0 in the middle. So now the next step is to do the non-dimensionalization. We're going to divide the concentration of species A by the surface concentration to get a dimensionless variable C. And we're going to define a dimensionless variable R bar as the physical radius divided by the outer radius, the radius of the actual pellet. A very brief reminder of how this works. 2 extra factors of r squared downstairs if you work through the chain rule. So you get dA effective over r squared. So now what we're going to do is we're going to multiply this whole equation by r squared over dA effective. So we'll just erase this from this, multiply everything through over here, and then I've got, all right. And then what we're going to do is we're going to take this little cluster of parameters and we're going to call it phi squared, okay? The squared Theile modulus. That's where this definition comes from, the Theile modulus. Okay, so this is a very important dimensionless parameter, and this is going to allow us to immediately look at this number. You notice that it's the only parameter left in the equation. If you go back over here, everything is dimensionless, and there's only one parameter in the equation. So that one parameter is going to govern the nature of the solutions all by itself. Okay, so we've arrived here at this equation, and it has just this one parameter, phi squared, the Theile modulus squared. And so the rest of this is just a math problem to go through and identify the nature of the solutions of this problem and hopefully put them to use. Remember our dimensionless boundary conditions, I'm not sure we really talked about this, but after non-dimensionalization, we want to do that to the boundary conditions as well. And they become that C becomes 1 at r equals 1. And of course, my dimensionless C derivative with respect to r is still 0 at r equals 0. So those are my boundary conditions. And the solution to this can be obtained by the method of Frobenius. Hopefully you can get to see that at some point in a differential equations class or in the applied math class here. So the solution ends up having this form. It's the sine hyperbolic of phi times our dimensionless r divided by sine hyperbolic of phi multiplied by r on the outside. When the Theile modulus is very small, the solutions show that the concentration penetrates all the way from the surface into the interior of the catalyst pellet down to the center. When the Theile modulus is very large, the concentration, the reactant concentration gets consumed before it ever penetrates beyond the outer skin of the catalyst pellet. Let's think about why that would be. Let's go back and remember what was the definition of our Theile modulus. So when the Theile modulus is very small, it means that the diffusivity is fast compared to the characteristic reaction rate. And that's why fast diffusion and slow reaction allows our reactants to penetrate all the way into the interior of the catalyst pellet. When we go to the other regime and the Theile modulus is very large, that means that the characteristic reaction rate, K cat times R squared, is much faster than diffusion. And now things are getting consumed near the surface of the pellet before they have a chance to diffuse into the interior of the catalyst pellet. Theile's recognized that you could kind of encode this whole solution into a really easy algebraic expression for the reaction diffusion problem. Okay, so the way that Theile encoded the solution to this reaction diffusion problem for easy use in all kinds of applications was to define this thing called an effectiveness factor. Where does the terminology come from? When the reactants do not penetrate down into the interior of the catalyst, then that portion of the catalyst is not being used effectively. Basically what you have here in this definition of eta, it's a ratio. In the numerator, we have the overall reaction rate when diffusion effects are included. And then in the denominator, we have the overall rate in the ideal case where there are no diffusion limitations. So under typical scenarios, the denominator will be the larger reaction rate, although there are examples for other kinds of rate laws and for heat transfer that we will encounter later. But usually what happens is that this effectiveness factor, eta, maxes out at a value of 1 when you're in that small Theile modulus limit where you get penetration of the reactants all the way into the interior of the pellet. When you're in the large Theile modulus limit, then the effectiveness factor becomes small because no reactants are reaching the interior of the pellet. Remember that Ca sub r, that's what we just solved for with those sine hyperbolic trig functions. And everything in the bottom here is just a polynomial integral. So these two integrals can both be done, and they result in a fairly simple function that you can write down in terms of a cotangent hyperbolic. And in terms of course, the one parameter in the problem, our Theile modulus. If we plot the log on a log scale, eta versus phi, this is the Theile modulus on the horizontal axis and the effectiveness factor on the vertical axis, then you see this orange curve. This is the complicated expression in orange. That's the 3 times phi cotangent hyperbolic of phi minus 1 over phi squared. So there are a couple of things to note about this. Of course, it goes to 1 when the Theile modulus is very small, indicating that there are no diffusion limitations. But also, there's a convenient expression when the Theile modulus is very large, and that's that it asymptotically approaches this 3 over phi limiting behavior. And in many cases, that is a really useful thing to keep in mind. It's easier to work with in the cotangent hyperbolic expression when you know that you have severe diffusion limitations.